So thanks for everybody for joining. Today here is hard to believe it's already November. Started to the end of the semester and the end of the calendar year too. But for today we have Deven Mhadgut posted up.
Yep.
Right.
That's good.
With another of our series of CubeSat 1 presentations. And without further ado, I will turn it over to you.
Just checking if everyone's able to hear me online.
Give a thumbs up online.
Okay.
Okay.
Yeah, I'm Deven. I'll be talking about CubeSat 1, the science objectives, and the dynamic characteristics of parabolic composite booms. I'm a PhD student working with Dr. Black. I also worked with one of his research associates, Dr. Davaria. And yeah, let's get into it. Some background on why we use these booms for deployable space structures. So I'm assuming you guys have already heard of deployable space structures, but then why specifically these carbon fiber booms? First of all, this is mainly a list of the advantages of these booms, and they are a viable alternative to these truss-like structures. So in the past, people have been using metallic booms for truss structures, and you can clearly see that these carbon fiber booms are lighter and cheaper compared to those. They also have the advantage of deploying certain systems which are noise sensitive, like magnetometers, away from the payload avionics. So we can protect these systems from the noise that we get on board. And then you can have optical and communication systems deployed accurately. So these are systems which need a certain level of pointing accuracy most of the time. And we believe that these carbon fiber booms are stiff enough to hold these systems in place and have certain level of pointing accuracy that they need. They can also assist in opening solar sails, as the one that image that I've attached over here on the side. That's ACS3. It's Advanced Composite Solar Sail System, which is a 6C CubeSat. And I think that's going to be launched next year, early next year, and it's being manufactured right now at NASA Langley. So these are again light and cheap, as I said already, and through that, they also help to save the fuel mass requirements of massive propulsion tanks and attitude control systems that these satellites require. So that was a gist of why we need booms. Coming to CubeSat, we are flying one of these carbon fiber booms aboard one of the CubeSats here at Virginia Tech called CubeSat. It's a 3U CubeSat. And one of the seminars in the past has already spoken a lot about it, but I'll go through the gist of it. And the main motivation over here is showing that these carbon fiber booms can be flown and deployed on a 3U CubeSat form factor as well. The main primary objective of this mission is showing that a novel design of a deployer, of a CubeSat deployer, can work. And that design was made here by Minzun and one of the other students in the team. And that's the main primary mission. And you can see right at the bottom of the slide, the design of it. And this boom that we are flying, it's not any boom, it's a bistable boom, which means that it can be deployed passively. It's like a wristband which slaps on your wrist and rolls around the wrist. So you can imagine that it can be deployed passively, but on the other hand, it needs to be retracted actively using a stepper motor. So we needed a certain design to hold the spool while it's not to be deployed like during launch or during certain operations, but then we would want it to be deployed passively and then retracted actively using a stepper motor. So that's the design. So that's the primary mission, and then we have the secondary mission, which is the science objective, and that's what I'm more concerned about. That's basically related to the measurement of the acceleration of the tip of the boom after it's deployed. So we have one IMU, or an initial measurement unit at the tip of the boom, and another inertial measurement unit inside the spacecraft chassis near the root of the boom to measure the acceleration. And I'll be talking about this in the rest of the presentation over here, but that's the main point. And the experimental requirements run down from this main science requirement. So it says that the experiment shall collect data till 5 seconds. So we assume that the deployment will take less than 5 seconds and will stabilize within the 5 seconds of the event. So that's why 5 seconds of data for per every experiment. And then we say that the experiment shall collect data for 200, a sampling rate of 200 hertz. That runs down from the fact that the natural frequency is around 5 hertz, and the Nyquist criterion, which is like a rule of thumb, says that 10 times the natural frequency is what we need for the sampling rate. And we actually have twice that, so that we can have sufficient noise clearance, which means that we can have enough data to chop off and to weed out the noise right after we get the data. And then the experiment shall also collect the distance of the boom. That will be through the cameras and the encoder on the spool. And the experiment shall be repeatable. Now the question is, why do you need this experiment to be repeatable? We will be doing it 4 times. Basically, we'll be doing deployment once and then deployment interaction thrice. And we need it to be deployable so that we can demonstrate that it can work for certain systems in the future which have multiple booms. And systems like antennas or even mirrors, which need pointing and maneuvering and gimbaling after they've been deployed. So we could probably retract ever so slightly, and the other boom could be deployed at the same distance so that we could gimbal the mirror or the antenna or whatever the payload is. But that's the main point of having it to be repeatable. This is again, this has already been spoken before in the previous seminar, but I just had this image here to give you an understanding of how the boom will be deployed on the side. And you have the camera right here pointing right at the tip of the boom. And this is an earlier design, but you will have the embedded cables running through the boom, and you will have the IMU circuit right at the tip of the boom. Again, this is about the mission of UtproSat, but the essence over here is that the end of life is, as it says, it's 2 days. So we need to collect. We only get 2 days, as predicted by this STK simulation, and we have to collect the data and transmit the data to the ground within these 2 days and 8 passes over the ground station. One of the future seminars will talk about the deployer and its evolution in detail. But 2 things to see over here. First of all, the deployer has evolved a lot, but the idea remains the same, where we clamp the boom at its root and at the center of its root, so that we can have the initial parabolic shape right at the beginning, even before it's deployed. And when it's deployed, it can easily deploy through its bistability. And then on the right, you can see even when it's suspended like a cantilever beam, it can still hold its own and not fall or roll, which means that it's stiff enough to even have certain circuits, light circuits, at its tip right now. So this is a short video of its deployment. And you can see that there's a jerk at the very end. So I'll play it again. So this jerk at the very end, which actually has an effect on the chassis of the deployer. That is what I am concerned about. Not the actual acceleration, but the transverse acceleration at the end of deployment, which actually has a jerk on the satellite chassis itself. So yeah, moving on to why we are testing the boom itself. So that was the CubeSat. This is why we are testing this particular boom. And the main point over here is it's a novel profile. It's not been done before. Previously, people have done and used circular cross-section booms, even closed cross-section booms, but none of them have done parabolic cross-sections. And we believe that there's a certain advantage in terms of the bending and the torsional stiffness for these conic cross-sections. So that's what we're trying to predict and prove that these conic cross-sections might have certain advantages in that sense. And then we are working with Penn State University for this project as well, where they help us embed cables or traces, copper traces, inside the composite of the boom. And that those traces will be used to transfer power and science data to and from the CubeSat chassis to the tip of the boom. And I'll be talking about it in a bit. And finally, the ground test data that I'm doing, and then the finite element validation that I'll be doing to correlate this data with the data that we get on board whenever we fly in March next year. But the paper over here at the bottom, that would give you more details about how the cables are embedded inside it and some of the tests that they did to prove the viability of these embedded traces. Now the boom itself, as I said, it's a parabolic cross-section boom, and it's bistable. The composite properties are given at the bottom over here, and it's got 3 layers. The first and the third layer are the same material, but uh, exactly opposite 45 and plus minus 45 plain weave carbon fiber. So the direction of the fibers is exactly opposite. And then in the middle, you have the 0 degree or the unidirectional carbon fiber, and that's where the embedded cables lie. So uh, you have, whenever you manufacture these booms, they lay up such that you can have the embedded cables co-located with the unidirectional carbon fiber, and the length of the boom is 4 feet. Again, if you need more information about the bistability and the criterion and how it's defined, how it's derived, you can go to the paper cited at the bottom. As I mentioned, we'll be collecting data on orbit, and that will be done through this flex circuit that's shown over here. Is this black spot, this black circuit, that's black IC, that's the IMU IC, and the tip of the boom will have an enclosed IMU, as it said, and a second IMU, which is not shown over here, will be inside the CubeSat chassis. So how we had initially planned this was we would have an active vibration source on board on the chassis itself, and that would excite the boom. But unfortunately, we couldn't do that. So we ended up having the input to the transfer function as the vibration of the boom itself, and the output being the effect that this transverse acceleration of the boom causes on the CubeSat chassis itself. So that's what we're doing right now, where the input to the frequency response function is the transverse acceleration at the end of the deployment, and the output being the effect on the chassis. So the boom, as I said, will not be excited by any active vibration source, but by itself. So through its own strain energy, it will be deployed, and that will cause a transverse acceleration. And that's how the boom turbine will be oriented to measure the shock wave at the end of the deployment. So it's not shown over here, but the traces go throughout the length of the boom, and they fold over at the tip. And these 4 small things, these are the traces. So this version of the boom had 4 traces on one side of the parabola, one arm of the parabola, but the final version will have 8 cables on each arm of the parabola. So coming down to the important ground tests that we were doing. So even though we are concerned only about the acceleration, this is something, modal analysis is something that's very important to be done right at the beginning of any vibration analysis. And in my case, it is essentially important because I'm also doing some finite element modeling for complex tests, and I need to validate my models, and I need to know that my models are really accurate. And that will only be done when I do the model analysis in a lab. And this is a simple test, so I could do it in a lab quickly, and again replicate it in finite elements and check if my finite element model is giving the same results, and then I can move on to complex tests in the finite element simulations. So that's the point of doing these modal analysis or basic vibration analysis tests. So as you can see, I've deployed the boom, fully deployed the boom, and it's pointed downwards. That's mainly to offset it from gravity. So the main acceleration that I'm concerned about is the transverse acceleration and not the axial one. So therefore, the transverse movement is not hindered by gravity in this case, and that's why the orientation is such. Uh, the deployer was fixed to an aluminum frame. The table over here is a vibration isolation table. It's not shown over here, but the table actually is held by these dampers, which are piston driven. So they isolate all the environmental noise, and you can have a cleaner vibration analysis done. and I used the scanning laser vibrometer to measure the velocity. So this vibrometer is based on the principle of Doppler effect. And if you remember from your high school physics, Doppler effect is where you can see a frequency shift or change in frequency on any light that's reflected off of a moving object. So that moving object will have a certain velocity, and the change in velocity and the change in frequency will be proportional to each other. So through the change in frequency, the frequency shift, we measure the velocity of this vibrating boom. And that velocity is actually the output in our case, and the input will be done through this small thing over here that's called a modal hammer. It's an impulse hammer, so you hit the boom with this hammer. That's the input, and you measure. This hammer also has a load cell on its tip, so that gives us the force and the velocity measured by the laser vibrometer shown on the right. That's the output. So that's how you get the frequency response function, and then the peaks in this frequency response function signify the modal shapes or the mode shapes, and those give us the natural frequencies of the boom. So that's the result out of it. You can see the first mode of this boom is 3.51 hertz. The second mode went 4.68 hertz. It's not exactly very clean data, mainly because the specimen under study, which is a boom, is extremely nonlinear. But at the same time, the modal hammer does not induce any external dynamics into it. So it is more or less as accurate as it can get. And that's what we are relying on, the 3.51 hertz being the first mode. And what we saw, and what is normally predicted for structures like these, is that the first mode is the torsion mode, and then you can get a bending mode, and that's what we observed in our experiments as well. So first mode was torsion, second mode was bending, and then you get first torsion, first bending, second torsion, second bending, and so on. So they alternate between torsion and bending, and that's what we saw. And we did the same thing with a shaker, just to see if we're getting the same results. And the shaker is basically this small thing which moves to and fro. And essentially what it means, or what it says, it's a shaker. So it shakes the boom, and there's a stringer attached to it. And it functions in the same way where you have the laser vibrometer over here pointed at the boom, taking the velocity output, and the input being this load cell attached to the stringer of the shaker. So it's basically the same philosophy, but you get much cleaner data. So that's the zoomed in version of the entire setup. You need an amplifier in most cases because the load cell input is very small. But yeah, so you can see it's much cleaner compared to the previous result. But there's a shift in the frequency from 3.51 to 3.59 hertz, and that's because the shaker like you can see that the shaker is not attached to the table itself, but it's attached to this frame which is attached to the table. So there's an addition of mass to the system which increases the natural frequency. It pushes it further. So that's what you see over here. There's a shift in the natural frequency, and those are the modes. So that's the first mode being torsion. You can see it being torsion, approximately torsion. It's not exactly and clearly torsion or bending, only bending, because the thing under study, as I said, it's non-linear. It can't be approximated as a standard cantilever beam. We wish we could do that, but it's not possible, especially because the shape and the material, it's a composite, so it's not just one material. So there are non-linearities involved. The shape is not a straight beam. So in the future, what we intend to do is even this simulation, it's not exactly the most accurate that we can get, but in the future when we have 3 laser heads, so you saw that we had only 1 laser head in this one, which means that it only measures vibration through Doppler effect in that particular plane. But if we want to scan the entire shape of the boom, to have that entire curved surface area mapped to this vibration analysis, then we would need 3 laser heads pointing in 3 different axes. So that's the plan right now. So we intend to do that soon enough, and yeah, we hope that it's more or less accurate. And then coming to what is really important for us, which is the acceleration. So when we were doing these tests, we did not have the final version of the boom, and the traces inside the boom were broken. So we couldn't use the IMU at the tip of the boom. So essentially, we ended up using the accelerometer in the lab, and we attached it to the tip of the boom, and we manually coiled the spool so that you can have the gravity and the boom strain energy working to deployed. So that's what we ended up doing, and the acceleration was measured by the tip of the boom accelerometer. So this is what we got. We measured it twice. The first one was throughout the deployment, and the second one was right at the end of deployment, which is what we're concerned about. So you can see that this accelerometer was a 3-axis accelerometer, so it can measure acceleration in all 3 axes. But the maximum one, you can see 168 and 229, that's along the axis of the boom itself. So that's along the length, and that's the axial acceleration, which we're not concerned about. So it's really big. But the jerk at the end, that's this 9.76 and minus 11.48. And you can see it being repeated as a pattern in the orange section, which is only at the end of the deployment. So that coincidence shows us that the accelerometer measurements were more or less accurate. Future tests would have these booms suspended using a gravity offloading system. So right now we are just doing it vertically, but we want to deploy the boom horizontally as well, so that we can have testing as we fly. So it's similar to the on-orbit conditions. And then we want to perform the modal analysis and acceleration tests using the IMU, of course, because right now all we've done is using accelerometers and load cells in the lab, but the final version will have the IMU. So this is one idea of the gravity offloading system. We've been thinking about multiple ideas, and we will try to implement it soon enough, where we have this carbon fiber boom suspended horizontally by these nylon strings and a soft spring. So you essentially have them suspended from one single point so that it allows for rotation in both the planes, in both the horizontal plane and the vertical plane. So that's how we fly, right? So there's minimum restriction, minimum constraint to its motion when it's deployed. And the spring essentially allows it to deploy. So the length of the nylon spring is fixed, but the spring can extend, and it can allow for the deployment of the boom. And we essentially use nylon strings because those are extremely light, and we don't want any inertial effects in our vibration testing. So they reduce the total mass of the system. One side thing that I've been working on is called the refined unified nonlinear formulation. It's a finite element technique. Uh, it's a fancy technique which is also based on finite elements, but specifically for slender structures like ours. It's like the carbon fiber booms that we use, or any of these long rod-like structures. And you can see this image on the right shows the conventional beam element, which has 3 nodes. Each node will have 6 degrees of freedom, so 3 translations, 3 rotations, and those give us 18 degrees of freedom for one beam element. But when we move on to these 2D run elements, as we call it, you can have different levels of refinement at different cross sections. So you can see that this one has lower refinement. So and you can have higher refinements at areas where which you are more concerned about. So areas where there are bends and there are buckling areas, or there's, you know, that it's going to fail at a certain location, you can have higher refinements. And you do that normally in normal FEM as well, but that requires solid elements and not 2D beam elements. So these solid elements usually increase the computational effort involved, and instead we use these run elements, which show that we can get the same results or similar results using a different way of refinement, and to a certain degree of accuracy as well. So that reduces the computational effort, increases its efficiency as well. And the final goal of all of this would be testing this data or getting this ground test data and getting the on-orbit data and finally validating this code with all this so that we can show that this novel technique is more or less accurate and can be used for other applications as well. So next steps in this process, as I already mentioned, we intend to use 3 laser heads for a better understanding of the out-of-plane dynamics. We'll be testing everything with an IMU. One other thing that we are concerned about right now is the other temperature effects or the effects of just going through the orbit, having different temperatures at different orbit locations. We'll be doing experiments while we are moving in orbit. So each of these experiments will give us a slightly different effect. And that's been shown by many people in the past, where there are certain effects of fatigue, certain effects of damping because of the expansion of the boom material itself. And it's a black boom, so it can absorb a lot of heat in space. So yeah, we'll be doing this in TVAC and see what effects we get. We are also flying the boom in a couple of days on a balloon, so we'll try to get that data as well. And the final version of the boom, the on-orbit version, will also get some temperature data so that we know at what temperatures we are collecting all this vibration data. And then again, scanning the boom system for getting a CAD model. So we've already done this in the past. We couldn't get an exact CAD model through 3D scanning the boom. So we ended up just measuring the boom at certain different locations and then interpolating and forming the boom CAD model for the FEM. But in the future, we intend to scan like a good 3D scan of the boom so that we can do all the FEM on that CAD model instead of the one we have. And yeah, finally, of course, when we fly in March, April, on the Cygnus 19 mission next year. Yeah, that's when we'll get the data and then we can compare it with the experimental values that we have. Finally, I would like to thank our project partners, Visa, Virginia Tech, of course, NASA for giving us these carbon fiber booms, Virginia Space, Penn State, and ODU. Penn State is helping us embed these traces, insert these traces inside the boom. So yeah, thank you everyone. Any questions?
I'll maybe ask one to start off. One point you kind of brought up towards the end and something I hadn't thought about before. Do you anticipate any kind of interesting effects where it goes to that TVAC part where your boom is here in sunlight, and if the body of the CubeSat is kind of is not black and basically shaded and cooler, and having that temperature differential always means that boom, which could be warm and absorbing. Do you think there's anything there? Is there thoughts on like testing anything or trying to get that?
Yeah, we will definitely have the boom deployed along with the CubeSat chassis, the entire chassis in TVAC. So that's definitely a plan in the near future, actually. So when we do that, I think we'll not only collect the data on the boom, but also the data on the temperature data inside the CubeSat chassis. So yeah, that's a good point. We'll have to think about it for sure.
Yeah, just thinking there would be somewhat of a temperature. TVAC, you can take everything down to a certain temperature, but what you might experience might be, it won't be all the same temperature. It could be a slightly different temperature differential.
Yeah, it's not just the vibrations, it's also the temperature effects, which will cause vibrations. So it's hard to imagine, but in space, over long periods of time, you have vibrations of extremely low frequency. And those are induced by the day and night cycles. Even though our mission is only 8 passes, it will still have certain temperature effects, and those will be really important for us.
Yeah. Cool.
Yeah, any other questions?
A related question. I was just curious, with regard to the test plan, does it factor in at all that, in flight, you're going to be in 0G and 0 atmospheres, and for your ground testing here, except for thermovac, you're going to be at 1G and 1 atmosphere? In terms of the deployment, especially the retraction, that just sounds hard to me. Are there any concerns with how you test that and verify it really works?
We've already done the things in TVAC, the deployment and the retraction. But yeah, you make a good point where we might not be able to exactly replicate. So the TVAC will have the required pressures and the temperatures, but yeah, the gravity factor of it might be really hard to replicate. And having the temperature and the pressure with the gravity offloading might even be impossible for us because of the size of the TVAC that we have. One thing we could do is do separate tests and just try to predict through just analytical stuff like maths if we could get the same results in zero gravity through simulations. But yeah, I don't think we could do it on ground where we have the gravity offloading done with the TVAC.
Which thermovac are you using? Are you using the one in Whittemore 6th floor or another one?
Yeah, we're using the one in Whittemore 6th floor, 619.
Okay, so that deployed sail fits in there.
It's partial deployment.
Partial deployment.
Yeah,
Yeah, we couldn't have the full 4 feet distance. I think
Okay,
I think the one in the lab downstairs, that might be bigger and probably we could have the full deployment. But I don't think it's working right now in 181, Durham 181.
Yeah, although we're going to talk to those guys, there's a chance in 6 months it might be. Even yeah.
Yeah, we would want to do it over the next month.
Yeah, say in 6 months for CubeSat will be for enough.
Yeah. Oh yeah.
Everything is the same.
Yeah, if we could do it over the next few weeks, then it's really important and useful.
No, that's not going to happen. That's too bad.
Yeah, that's right. But yeah, the partial deployments should give us some idea of what kind of thermal data that we get and pressure data as well.
Mhm.
And NASA can also provide more booms of the same one after the mission.
Oh yeah. We can definitely do the tests after this mission. We can continue with our tests, and this might not be the last. So it's called UltraSat 1. So we hope that we can have future CubeSats and future missions. So even if we are not able to do the entire full-scale test for this one, we probably do it for the next one for sure.
Yeah, to me, I was thinking, like I really appreciate all your modeling, right? That is actually really well done. I just think more of the, how do you test to make sure that the system you're flying is what you modeled, right? So it's more of a functional test, right? To do that way, right? Test as you fly, right? This is something you can't test as you fly, right?
Yeah.
So I'm wondering, if there's any concerns there or any way you can get at that to make sure it's going to be okay, right? This is to fold that thing back up, right? Is actually pretty sophisticated for this type of spacecraft, and you're gonna, really hit that thing hard on launch, and it's still got to work after that. So I'm just kind of curious, what's the best you can do to come as close as you can to test as you fly?
Yeah, I think we could do extensive vibration tests where we put the entire thing on a table and vibrate as hard as we can to replicate the launch loads. Yeah, it's just the gravity offloading that we might not be able to do. I mean, we can do gravity offloading, but not along with the TVAC. I think that's the main issue.
Yeah, no, I understand. Okay, thank you.
Yeah. So I was saying the retraction will be done by a stepper motor, and we've already done that multiple times. But I understand your concern. Like through vibration, there is a chance that the stepper motor stops working or something.
Oh yeah, and even stepper motors are sensitive to environmental changes or temperature differentials that, you know, you're doing a thermovac, so you'll know what the temperature of that stepper motor's operating at if you can simulate it right, so you can test your model. Just all those things add up. You know, we used to have a reviewer on the Snowy project, and we were flying a stepper motor on there. And every time we had a review, he's going to say, "What if you get the stepper motor with a grain of sand in it?" You know, you know what he really meant was, how can you really test to make sure, right, that it's going to work exactly in space as you have it on the ground or as you intend to.
Yeah, I'll definitely think about this.
Yeah, this was very impressive. The level of modeling you went to and the thought behind it. This was really good.
Yeah, thank you.
Mhm.
Yeah, certainly too. I so wanted to say that's a really neat idea on the, you call it the goals. The gravity
Yeah.
upload. It's a really neat, idea. I don't know if you've seen anything like that before, but it is sort of my experience. So, yeah, any other questions out there? Before we close down. Going once, twice. All right, nothing heard, so thanks everybody for joining today here. And as I put in the email, we have two more. As I say, we're eyeing towards the end of the semester. We have two more projects for the or two more seminars rather for the series or for the semester as the word I'm searching for. So if you would like to present, feel free to email me as soon as possible. I think maybe how you and Vincent are going to try to take one of them.
Vincent and I will present, but I think we're present after delivery.
Okay.
So it might be after Christmas.
Okay, so maybe in the next semester. Okay.
Yeah,
that sounds good.
Because I think it will be good to show like the full. Okay, so then delivered.
Yeah.
And then it closes up with.
Yep. Okay. Yeah, so anybody has wants to present, please email me as soon as possible, and we can get you on the schedule. But otherwise, hopefully we'll see everybody in 2 weeks. And thanks for joining us.